Welcome everybody to another Quantitative Methods Network or QMNET talk here at the University of Melbourne. My name is Mike Zephyr and I'm an associate professor in the Faculty of Business and Economics. And today we've got a really exciting talk by one of our own. Mingming Gong here is going to talk about bridging causality in learning or machine learning and how do they benefit from each other. Now, Mingming, let me just say a few words about you. Mingming Gong is a lecturer in data science with the School of Mathematics and Stats here at the University of Melbourne, and he's affiliated with the Melbourne Center for Data Science, as am I, and a few other people who are in attendance here. His research interests include causal inference, machine learning, computer vision. He studies how the causal generative process of data benefit machine learning, such as transfer learning and weakly supervised learning. He also, which pretty much sums up my orientation towards my kids over lockdown. He also studies principles and methods to infer causal models from various kinds of observational data, including undersampled time series, data with measurement error, non-stationarity, and heterogeneous data. So in other words, regular data that we come across all the time in the social health and other sciences. And he's authored and co-authored more than 30 research papers in various top venues, ICML, et cetera, and has served as a senior program committee member of AAAI and IJCAI. So Mingming, thank you so much and congratulations again. It's an honor for you and all of us whenever somebody gets a DERRA, especially studying something so important. So thanks again and feel free to take it away.
Yeah, thank you, Michael, for the introduction, and thank you all for coming. So today I'm going to present some of my research works at the intersection between causality and machine learning. So, sorry, So currently, deep learning method is the state-of-the-art technology in artificial intelligence. So with the deep learning methods, we can do lots of things like recognize objects from images and also recognize species and text. So if we look at a typical machine learning system, so for example, the most classical one, which is called supervised learning. So in this supervised learning setting, we usually have two variables, x and y. And x is called the input features, y is the label. And by drawing some data from the joint distribution of these two variables, we can get a data set. Then we want to predict, if we want to predict the future observations of x, so predict the labels, we can use a neural network to model the conditional distribution of PY given x. So this one encodes some functional or probabilistic relationship between the two random variables, such that given a new observation, for example, image input, then we can get its label. So this is a very powerful method, so it has many applications in different domains. So here I'm going to introduce a very famous example. So in this example, we don't have many complicated variables like high-dimensional vectors. So we only have two random variables, and both of them are one-dimensional. So the x-axis is chocolate consumption in one country, and the y-axis is the number of Nobel laureates in that country. So clearly you can see a strong linear correlation between these two random variables. So if we want to predict, for example, the number of Nobel Prizes in one country, we can use chocolate as a predictor to build a linear regression model. But sometimes the government may be interested in another problem. So basically, should we encourage people to eat more chocolate such that the country could win more Nobel Prizes? So this question seems much harder to answer because here we want to establish some causal relationship. So because we want to, if the chocolate consumption is the cause of Nobel Prizes, then we should encourage people. At least we can try to encourage people to eat more chocolate. But this might not be the case. So for example, the socio-economic status of a country could be a common cause of these two variables. So in this case, if you choose to eat more chocolate, so this will have no influence on the number of Nobel Prizes. Okay, so the reason why we care about causality rather than just correlation is that we want to make changes to the world. So for example, you can establish a causal relationship between the emission of CO2 and the global warming, then we can probably reduce the production of CO2 such that we can lower the temperature. In medical science, if we can establish some causal relationships between genes and some disease, then we can perform some gene therapy to kill that disease. So let's make the previous statements a little bit formal. So basically, the main difference between correlation and causality is that in correlation, we care about the dependence between the random variables. So for example, in machine learning, we usually care about this conditional distribution, where X is usually a feature, Y is a label. So given a new observation of X, we can predict its label. But in causality, we're interested in another quantity, which is called the interventional distribution. So basically, what's the difference here is that here we have introduced a dual calculus. So basically, we can set X to a new value such that we can observe the outcomes in Y. So here, powered by Juniper, so Juniper introduced the causal framework. So basically, we can use the graph to represent the causal relationships between the random variables. So here I show three very simple examples. So where the first one, X and Y are, so if there's a link between two random variables, which means there's a direct causal relationship between them. And if the causal direction means the causal influence direction. So for example, this arrow means that X is the cause of Y. And in the second figure, Y is the cause of X. In the third one, this Z is a common cause of both X and Y. And then we can calculate this interventional distribution after we set this variable to some specific values. And we can see that only when X is the cause of Y, so these two quantities are the same. In the second and third case, so they are not the same. This is because, for example, in the second case, Y is the cause of X. So this means if you manually set X to some value, this will not change the distribution of Y. And similarly, in the third case, because Z is the cause of X and Y, if you change the distribution or change the value of X, this will not influence the distribution of Y. So we can see the difference between the interventional distribution after we manipulated some system and the initial distribution in which we just observe some values and predicted others. Okay, so in recent years, there's many works appearing in the intersection between causality and machine learning. So for example, in causality, classical problem is to estimate the causal effects given some distribution or some data from the distribution and the causal graph. In this case, we want to estimate the causal effects. So in recent years, there are many works trying to make use of machine learning algorithm to estimate this effect. And another problem in causal inference is causal discovery. So in this causal discovery problem, we aim to learn a causal graph from the observational data. And in this case, machine learning also plays a very important role. So later I will give you some examples on my previous research projects. And the other direction is causality for machine learning. So this is also a vibrant area. So in recent 2 years, I think there are lots of works trying to make use of causal models or make use of causal knowledge to facilitate machine learning in different scenarios. So for example, in transfer learning, reinforcement learning, fairness, etc. So today I'm going to just talk about my research along these two main directions. So this is outline of my talk today. The first part is about causal discovery. So how we can connect machine learning with the causal discovery. And second one is called domain adaptation. So in this domain adaptation is a specific transfer learning setting. And I will show how the causal models could help in the transfer between different domains. Okay, let's start the first part. So a golden standard way to establish causal relations is to perform randomized controlled experiments. So for example, in the chocolate Nobel Prize data, we want to figure out whether X is the cause of Y or whether there's common cause between X and Y. So one way to establish or to distinguish between these two models is to conduct randomized experiments. So in this experiment, we can randomly assign the countries to 2 groups. And in the first group, we force people to eat chocolate. In the second group, so we force people not to eat chocolate. And after several years, we can measure the average number of Nobel Prizes in the 2 groups. So if they are significantly different, then we can say that, oh, so this chocolate might be a cause of the number of Nobel Prizes. So probably chocolate can improve our IQ in some way. But if it's not the case, probably there are some common factors or hidden factors which influence both variables. But in practice, these randomized experiments are often expensive or infeasible. For example, here, it's not sensible to make people eat or not eat chocolate. So causal discovery is a very interesting problem. So it aims to learn the causal graphs or causal relationships from observational data. A typical method in causal discovery is called constraint-based search. So in this type of method, we're given a data set. We can first perform some independent tests to establish some independence or conditional independence properties. So for example, here, from the data set, we can suppose we can find these properties. So x1 and x3 are independent. x3 and x4 are independent condition on x2. Then we can start from a fully connected graph, and under some assumptions like Markov conditions, we can fine-tune this graph according to the independence properties. So for example, x1 is independent of x3, then there must be no link between these 2 variables. So we can remove this one. And x1 is independent of x4, dependent on x2. We can also remove this edge. And similarly, we can remove this edge. So now we can get a skeleton, which represents the correlation between the variables. Our next step is to orient these edges to represent the causal directions. So here, the first one says that x1 and x3 are independent. Then the edge direction must be from x1 to x2 and x3 to x2. And given these 2 edge directions, we can find that the final, so this edge should have this direction from x2 to x4. Then we can find this causal graph from observational data. But the problem with this method is that the solution of this kind of method is usually not unique. So suppose we have a true causal graph which looks like this. So y is the cause of x is the cause of z. Then from this one, we can establish this conditional independence condition. So y and z are conditionally independent given x, because x blocks these parts. Okay, so now we have this skeleton. So we can remove the edge between y and z. We can have this skeleton. But in this case, we cannot determine the edge directions. So there are 3 possible solutions, which are in the Markov equivalent class. So another type of methods, which is pioneered by Schmidt in 2006. So we can, if we are willing to make more assumptions in the generating process. So for example, if we assume the variables has a linear relationship, and also the noise in the system is non-Gaussian, then we can get better, much informative results. So here I just show a very simple example. So in this example, we have 2 random variables, x and y. Now we suppose the causal direction is from x to y. So y is represented as the function, a linear function of x plus some random noise. And according to this causal direction, so this noise, E and X, are independent. Okay, so now let's fit a linear regression model in the causal direction. So we can find that the estimated error term and X are independent. But when we fit the model in the reverse direction from Y to X, okay, so this error term, estimated error term, and Y are also independent, or uncorrelated in this case. So this is when the noise is Gaussian. So this means when this is a linear Gaussian system, we cannot distinguish between these 2 directions, because the error terms, or estimated error terms, and the input are always both independent in the 2 directions. But if the noise is non-Gaussian, for example, if the noise is a uniform distribution, then we can find that in the causal direction, the estimate error EY and X are independent. But in the reverse direction, these two variables are not independent, although they are uncorrelated. So this means in this case, if the noise is non-Gaussian, we can make use of this property to figure out or to determine the edge direction. So we can find the causal direction. So this model can fully identify the causal model from observational data. Okay, so the third type of methods is called granular causality. So in this model, we assume we have some time series data. So basically, we can make use of the temporal information to help us determine the edge causal directions. So for example, in granular causality, a basic principle is that future cannot cause past. So as you can see from this picture, there's a time-lag correlation between X and Y, and X usually happens before Y. So it's likely that X is a cause of Y. And in the worst case, we can at least remove the filter out this case Y is the cause of X. Okay. So we can represent the model using a graphical model. So basically, these edges represent the self-influence, and the red edges represents the causal relationships between, for example, here from X1 to X2. So if we assume the variables have a linear relationship, we can use a vector orthographic model to model this data. So here, X at t time step t plus 1 is the linear function of X at time step t plus some independent noise. And this matrix A encodes the causal relationships between the random variables. So here, this 0.3 represents this red edge. So it's an causal influence from X1 to X2. Yeah, it seems that we can simply make use of granular causality to figure out all the causal directions. But the problem, a practical problem of granular causality is that this method is not invariant to the temporal resolution. So this means the discovered causal graph or causal relations are different at different time scales. So here is an example in neuroscience. The neuroscientists, so they're trying to estimate the causal relations from these brain regions. And recently they increased the image resolution and found more causal relations. So for example, if we set temporal resolution to 1 second, so that the algorithm cannot find any causal relations. And if we set it to higher resolutions, so for example, when temporal resolution is 0.1 second, then we can find many causal relations between these brain regions. Okay, so now we can, if we apply, this means if we apply granular causality on the data collected from at the low resolution or wrong resolution, we may get wrong results. And in practice, given data, we don't know whether this data is of low resolution or not. So this becomes the first work. So here we consider a problem of discovering causal relations from low resolution data. And we consider two cases. The first one is the subsampling. So in the subsampling scheme, suppose we use X to represent the high resolution data and X tilde to represent low resolution data. Then so this, suppose we are given a high resolution time series, which is not observable. So what we can observe is X tilde. So here, X tilde is obtained by taking just one value of every k consecutive X values. So for example, here, for simplicity, we just take the first value. So X1 tilde is X1, X2 tilde is X k plus 1. And if we assume this high resolution data follows a vector orthographic model, then we can derive a model for this low resolution data, so which is here. So this This model also is also a vector autoregressive model. And the only difference is that here the noise term is more complicated because it's a mixture of original noise at different time steps. And similarly, we can consider another scheme which is called aggregation. So this could be the case in economics, for example, in GDP data or house prices. So here, for every k consecutive values, we only record the average or the sum of the values within some time period. And similarly, we can derive the model for the low resolution data, for the aggregated data here. And this model is a autoregressive moving average model, so which is even more complicated. Okay, so now suppose we don't know the time series of low resolution, we just apply granularity on this kind of data, what will happen? So we can only get estimation of a to the power of k. So we can get this estimation. We can estimate this part, but a to the power of k can be very different from original matrix A, and it tends to vanish as k goes to infinity. So let's see a very simple example. So another thing is that in the aggregate case, as k goes to infinity, so we can use this instantaneous model to approximate this process. So this means when k is very large in aggregated data, the time lagged correlation of causal relations will become instantaneous relations. So here, both sides, we have the same time step. So now let's look at an example. So suppose the original matrix A is this one. And if we set k to 2, which k is the subsampling or aggregation factor, then we can see that this causal relation could disappear in this case. So this means we cannot simply apply granularity on the low resolution data. Then the problem is, can we recover the causal relations A matrix from the low resolution data? So before introducing our main results, I first introduce a concept which is called identifiability. So in this example, we don't know the high resolution data, so we have this low resolution data. And suppose we know some generating process. So for example, we have a model A. A represents the causal relations in high resolution data. And in high resolution data, we can, after applying the subsampling scheme, we can get this low resolution time series. So if from the low resolution time series, we can get the original model A, then we call this model is identifiable. And if we can get multiple solutions which can explain the data equivalently, so which means these three models can explain this data well, then we call this model not identifiable. So basically, we cannot get the original model. We cannot recover the original model from this low resolution data. And it has been shown that this A matrix is not identifiable if error terms is Gaussian. But in practice, in many systems, the noise terms are usually not Gaussian. So we can make use of this property. So then it comes our main results. So let's just first look at the subsampling case where we have derived a model for the low resolution time series. And if we assume the noise terms are non-Gaussian, so the first one is system is stable, so all the eigenvalues of A is smaller than 1. The second one is the most important assumption. So if the noise terms are non-Gaussian, and then we can prove that in general, this A matrix can be uniquely determined from subsample data. So this means if we can fit a model on this kind of low resolution data, in theory, we can estimate or we can recover the original causal influence matrix for the high resolution time series. And similarly, we get results for the aggregated data. And what's interesting here is that even for infinite k in the aggregated case, even when k is very large, we can still make use of this approximate model to get some information from this A matrix. So the exact condition is that we can recover the non-diagonal values of this A matrix. So at least we can determine whether a non-diagonal entry of A is 0 or not. So finally, after establishing these theoretical results, we can make use of standard machine learning algorithm to estimate the model parameters. So for example, here, we draw the graphical model for the two aggregated models. So this is one for the subsampled data. This is one for aggregated data. So here, these noise terms are considered as hidden variables. So we can use expectation mathematics algorithms to estimate the model parameters. And because these noise terms are non-Gaussian, then we can use approximate inference algorithm like Monte Carlo, Markov chain Monte Carlo to sample the posterior. So this is pretty standard. Okay, so let's see some simulation results. So here we perform experiments on some simulated data. So here we only consider 2 time series. And so the first 2 methods are our method with non-Gaussian noise. And the second one is a method with Gaussian noise. So we can see that our method can get a very good estimation of the true M matrix, while the model with Gaussian noise cannot. And these 2 methods are the 2 traditional methods in economics. So these 2 methods try to first interpolate the data, and they apply granularity on the interpolated data. And to show why the non-Gaussian noise assumption is important, here we show this likelihood landscape of the log likelihood. So we can see that if the noise is Gaussian, we have 3 solutions, which gives you the same likelihood values. So which means we cannot distinguish between these 3 models just from observational data. But if the noise is non-Gaussian, we can only get a unique solution. So this one is a unique solution, which corresponds to the true solution. And we also apply this method on some real data, for example, in temperature ozone data, where we have the ground truth. So here, the daily temperature is the cause of the ozone density. And in practice, because we don't know the K value, so the subsampling or aggregation factor, so we can use cross-validation to find this K value on real data. And here we can see that when finally our algorithm select K as the subsampling factor, and in this case, the causal influence from x1 to x2 in the reverse direction is the weakest. And similarly, we would perform the experiments on simulated data and real data for the aggregated model, where our model also showed a better performance. Okay, I will just skip this part. Yeah, so this is how we can make use of machine learning to do causal discovery. So basically, we can after we establishing some theoretical results on identifiability, then we can use the standard machine learning algorithms to help us estimate the parameters. Then we can make sure that the estimated parameters really correspond to some causal relations under the assumptions. In the second part, I'm going to show how causal models is useful in machine learning, especially in transfer learning. So first, I'm going to introduce this problem setup. So domain adaptation problem is extension of the standard supervised learning algorithm or supervised learning setting. So in this problem setting, we have 2 domains, where the training domain is called the source domain, and the test domain is called the target domain. So in the training data, we have both features X and the labels. So these colors represent different labels. So we can train a classifier to classify these data points. In the target domain, we only have the features, so we don't have any labels. And then if the distribution in the 2 domains are different, so for example, this is the classifier in the target domain, so they are different, then we cannot directly apply the classifier trained on the training data to the target domain. So because of dataset bias. Then our aim is to find the optimal classifier in the target domain, so which is a very challenging problem, because without proper assumptions or understanding of the data generation process, the solution of POY given X in the target domain is not unique. So we can find other classifiers which can also explain the data well. And this learning technique is very useful in many applications. For example, in computer vision, we want to transfer models from trained on synthetic data from computer games to some real data, for example, to estimate the depth values, to estimate how far a car is from the current car. In the medical imaging, we have different modalities of images. So, and we know that labeling these images are very expensive. So if we can transfer a model, what's here is a segmentation model, which can segment the organs in the MRI image, transfer this to some CT image, this could save a lot of human labor. Yeah, so as I just said, so this problem is very challenging. Without proper assumptions, this problem is generally intractable. So in the current previous works, a common assumption is called the covariate shift. So in this case, it factorizes the joint distribution between the feature and the labels as this. So as a product of P of X times POY given X. And it assumes that this one does not change across domains. This one is same. So only change happens in this marginal distribution of X. And if this assumption is true, then we can immediately solve this problem. So for example, we can use the instant reweighting to get an unbiased estimator of the target domain. So this one is our objective function in the target domain. And if we use this ratio, so these two are equal, so which means we finally train the classifier using the source domain data, and by just taking consider this weight here. Another type of method is trying to find some invariant representations from the original input features. So here, suppose we can have a function which can extract some invariant feature from X, which is called X prime, such that the distribution, the marginal distribution of the P of X prime are the same across domains. Then we can also solve the problem. But so one main drawback of this kind of method is that first, we don't know whether this assumption makes sense, right? So for example, if we observe that P of X are different in two domains, why should we say that these two are the same? And second one is that in some cases, this conditional distribution can also change across domains. And in this case, can we also do something? Okay, so before introducing our method, I'll first give you a brief review of modularity property of a causal system. So for example, we can have a causal model of the given data. So in this example, we have several variables. Suppose we have already known the causal model. Then, if we intervene on one variable, so here, if we change this variable, so if we set this variable to a specific value, so this one will only influence these two edges. So these two edges will be cut off. And all the rest will remain the same. So this means if we have a causal system, the change in the distribution is usually local. So here it only changes this part, but it will not change for example, the conditional distribution of gas level given gas connected and gas not. And we can also extend this to software intervention. So basically, software intervention means that instead of setting flame to a specific value, we just change the conditional distribution of flame given its two parents. And similarly, if we just change this conditional distribution in this part, so this will not influence the conditional distribution of gas level given gas connected and gas knob, and it will also not influence meat cooked given flame and meat on. So this one is called the modularity or independent mechanism of a causal system. Okay, now we can start building the model. So in our model, first we need to assume that the causal model is rather stable. So it's more stable than a distribution. So basically, if we get data from multiple domains, we assume that the underlying causal model is the same across domains. And the other one is just the specific case of independent causal mechanism. So suppose we have just two variables. The first one is cause, the other one is effect. Then the process of generating this cause, which is P of C, and the process which generates effect from the cause, which is P of E given C. So these two processes are irrelevant. Basically, without any other confounders, these two processes do not contain information about each other. Okay, now we can derive some domain adaptation scenarios. In the first case, we assume feature is the cause of Y, such that we can factorize the joint distribution along this causal direction. So the first one is P of X, which represents the process that generates X. And the second one is a process that generates Y from X. And these two processes are irrelevant. Okay, in this case, we can understand why covariate shift can be a valid assumption in some cases. So suppose there's some hidden factor related to the domain, which changes this distribution. So it changes the marginal distribution of X, and it will not influence this distribution because these two processes are independent. And similarly, we can have other scenarios. So for example, the domain only changes this conditional distribution, and this one will also not influence this part. And finally, if the domain change both distributions, then their change must be independent from each other. So in the second case, in the second and third case, we cannot find theoretically, we cannot find the P of Y given X in the target domain with just one source domain because these two distributions are not relevant. And in the target domain, we only have this distribution. So this one will not give any information to help you find the P of Y given X, Y given XT in the target domain. Okay, but in practice, Y could also be a cause of X. So for example, your medical diagnosis, the disease is usually cause of some symptoms. And in handwritten digit recognition, the digit we want to write the usually cause of the images we actually obtain. So in this case, we consider this process where the joint distribution can be factorized as P of Y times P of X given Y. So now P of Y represents the mechanism which generates the labels, and P of X given Y represents the mechanism which generates image, for example, images from the labels. And these two processes are independent. Okay, now we can also have some scenarios. So first one is called target shift, where the domain only changes the marginal distribution or the class prior distribution. So this part changed, but this conditional distribution remains the same. And if you look at the image, this means that the class level proportion could change across domains, but the image appearance, so for given a Y, given a 0, they will look the same in the two domains. And in this case, if we look back in the reverse direction, if we look at the distribution of X and the distribution of Y given X, these two will both change across domains. So this looks like now the classifier also changed across domains. But in this case, because these two changes are coupled, so finally we can find this P of Y by looking at the difference in the marginal distribution. Finally, we can correct the shift in the conditional distribution, such that in this case, we can find the optimal classifier in the target domain. And the other one is that called conditional shift, where the class proportion is the same, and the conditional distributions are different. So for example, the zeros or ones look different in two domains. And this will also cause a shift in the classifier. And in this case, under some assumptions, we can also recover the conditional distribution in the target domain. So later I will show our method. And finally, these two distributions could both change, but the change are independent. Okay, so now comes our method. So first, we assume that we have m domains, where m is the number of domains. And we use the theta to encode the randomness of the domains or the changing parameters. So each domain is associated with the value theta m. And here we can look at the model here. So here, this is the causal model where y is the cause of x. And in each domain, we have a theta m parameter. So so this theta m is shared across all the data points in one domain, and different for data points in different domains. So basically, this theta m encodes the difference between the domains. And the commonness between the domains are encoded in this function, so in this conditional function, and by another set of parameters phi. So if we use a functional causal model to represent this, it might be more clear. So we assume that, so to model this conditional distribution of x given y, so basically it models the generation process from y to x. So we can use this functional model where we have y labeled as input, we have some random noise to account for the randomness. We also have a latent variable theta. So this one represents the domain knowledge or the domain difference. Now here is the functional form. So basically for the mth domain, we have the x is generated from this function, where this function is a shared function across all the domains. So theta m represents the domain difference. So if we remove this theta m, then all the domains will have the same distribution. Okay, so let's see whether such a model could help us to recover the conditional distribution in the target domain. So let's see a very simple example. So here we have, suppose we have two source domains where we have the labels. So here, the shapes of the points represent one domain. So there are three domains, and there are two classes. So the colors represent different classes. So in the source domains, we have the labels. In the target domain, we don't have the labels. And if we just look at the target domain, look at this one. So we know that the function, the deletion function to classify data points, then infinite number of such kind of classifiers, because we don't have extra information. But if we also look at the source domains and we assume some change in the distribution, for example, the change in the linear subspace. So for example here, so this class will change along this direction, and this class will change along this direction. Then, by making use of this kind of change information, we can find the true conditional distribution. So this cluster might be the first class, this one might be the second class. Then we can find the classifier in the target domain. Okay, so based on this idea, we can train this model on for domain adaptation of the two or multiple domains. So here is an example when we have only one source domain and one target domain. So in the source domain, we have the labels and its corresponding images. In the target domain, we only have the images without labels. Okay, so in the source domain, we can train a model which can model the conditional distribution. So basically, given y, for example, y equals 0, we can generate 0 images. Given 4, we can generate images of 4. In the target domain, we can also generate this one. But the problem is that in the target domain, we don't have labels in the real data. So basically, we cannot match the sample data with the real data. So here, we can only match the marginal distribution of the general data to the target domain real data. So this means here, so only by matching this one is not guaranteed to find this conditional distribution. But by leveraging the information from the source domain, by leveraging the commonness and difference, so we can see that the model can find this conditional model for the target domain. So basically for 0, it will also generate images of 0 in the target domain style. So we apply this on more data sets. Here we have 4-digit data sets, and each data set could have different characteristics. And in this example, we have the first 3 data sets as the source domain, and the last one as the target domain. So in the target domain, originally we don't have any label. But in the source domain, we have labels. So basically, so these are generated images. So this is the image generated from our model, so which looks very similar to the true model. And here, so we can see that in the first row, it generates image of 0, right? This is not surprising because in the source domains, we have the labels. we can conditional the label and generate the corresponding images. But in target domain, we don't have labels. But as we can see, even we don't have labels in target domain, by leveraging the information from the source domains, we can generate correct images in the same row. For example, in first row, we can also generate 0. In last row, we generate 9. So which means that our model can recover the conditional distribution of each class just from the marginal distribution from the unlabeled data. Okay, and if we look at the classification accuracy, so our method basically beats the previous method by a large margin. So for example, in the second case, the previous method, best method is 66% accuracy, and our method is nearly a 90% accuracy. Okay, so last part. So in this case, in the previous example, we only consider a simple model which only have 2 random variables. But in many problems, we could have a complicated graph which involves causal relationships between multiple random variables. And so suppose we can divide the feature set X to some subsets, and we can have a causal graph among these subsets and the labels. Then we can further simplify this learning procedure. The first one, we can find the Markov blanket of these variables. So basically, we can ignore all the other variables because conditional on the Markov blanket, the label, and all the other variables are independent. And the second one, then because now we can separate these features, so we can find in the invariance and the changing properties of each module. So for example, from the multiple domains, we can determine which module is changing across domains. So here, finally, we can find that, oh, this distribution Y does not change, and the conditional distribution of X1 given Y and X4 does not change. But these 2 modules, so X3 given Y and X1, it changes across domains. Then we just need to associate a latent variable theta to these 2 modules. And for each module, we can separately train a generative model. So for example, here, we only need to train a model with X1 as output and Y. So X3, sorry, should be X4 as input. And because this module does not change across domains, so we don't have the latent variable theta. And for the changing module X3 is given Y and X1 and some random noise and theta 3 because so this theta 3 encodes the changing information of the distribution. So finally, we can train these models separately, so which can further improve the computational speed. Okay, so we apply this method on the Wi-Fi localization dataset. So in this dataset, we want to localize a person in the hall by monitoring the Wi-Fi signals received from his or her phone. So in this case, we consider the transfer between different time periods because in different time periods, the distribution of the signals are different. So they have different distributions. And if we can transform from one period to the other, then we can build an adaptive model, which can adapt itself all the time. So here we will collect data. So the data were collected at 3 time periods. We want to consider the transfer between, for example, from T1, T2 to T3. And the first step, because in this case, we don't have a color graph from for example, from background knowledge. So here we make use of a multi-domain color discovery algorithm to first discover a color graph between the Y and the features. And the second step, in the second step, we can apply our method to learn the conditional model of each color module. Okay, so finally, we can find this. Our method also achieves very good results, much better results than previous methods. Yeah, so here is conclusion. Basically, machine learning helps discover causal information if we can establish some identifiability conditions. So under this identifiability condition, we can guarantee that the learned correlation might correspond to some causal relation. And the second one is that the causal information could benefit machine learning in some non-standard settings. For example, for the non-stationary cases when the distribution could change across domains. And there are also many other examples in reinforcement learning and, for example, fairness learning. Okay, so this is the end of my talk. So finally, I'm going to briefly introduce my DERRA project. So it's called the Code Discovery from Unstructured Data. So as you can see in my previous works, I usually consider very low dimensional vectors. So basically, one variable is just a one-dimensional variable. And in practice, we may have unstructured data. For example, we have text, we have image, we have some, for example, DNA, which can be represented as graph. We have other kind of signals. So from this kind of different modalities of data, if we still want to discover the causal relations between these random variables, we cannot simply apply the previous methods. And here we can see some challenges. First, if we use the conditional independent test to find the graph, then based on these variables, which are usually unstructured and high dimensional, the conditional independent tests usually have a very low power. So in this case, we need to try to learn some representation while we do independent test. In the second case, if we consider the functional causal models, so for example, in my previous low resolution time series, so we assume each variable is just one-dimensional. So we also assume the relationships are linear. Then we can just use a matrix to represent the causal relationships. But in practice, if X, for example, X is image data or some features extracted from image data, then we cannot simply use this kind of metric to represent or learn this kind of causal relations. So in this case, we need to develop a new functional causal models which can account for this kind of unstructured variables. And finally, because the variables are very high dimensional, so we need to reduce the computational complexity. Yeah, so this is my talk today. Thank you for listening. Yeah, any questions?
I think
Sorry.
you're muted, Mike.
Yeah, go ahead. Go ahead, Simon.
I was just going to tell you you were muted. But...
Oh. Thanks. I was just saying, thank you so much. That was really interesting. And let's open it up for questions.
So if no one else has one, I might throw in a question just to get us rolling.
Yeah.
So thanks for the talk. It was very, very interesting. One of the things I thought was very interesting, the analysis of the range of causality and the impact of the resolution of the signal layer, and in particular how that kind of gets compromised as you increase the resolution. So one of the things, and I haven't really been able to think this all the way through, but so you know that there's other methods like convergent cross mapping and so forth, which is part of this this empirical dynamic method. Now, I'm trying to think about whether that would be susceptible to the same issues.
Okay. Yeah, so this, I don't have a definitive answer because I'm not very familiar with that.
Yeah, oh, we might just need to leave that one to future research, but my instinct is that it's not as problematic because you're looking at the correlation across of these correspondences across, well, firstly, in the first instance, it's happening simultaneously as opposed to being a predictive model.
Yeah.
But then you're looking at the correlation across the entire data set as you increase the size of the data set.
Yes.
So I think my instinct is that it's not susceptible to that, but I'm not 100% sure.
Yes, so here we say causal relation because we have temporal resolution, temporal information.
Yeah.
So, yeah, so because, so here Another assumption is that we need to assume the system doesn't have any other unobserved confounders. So for example, if there's a unobserved time series which influence the other observed time series, then we cannot simply say that the time-lag correlation corresponds to causality.
Right. Yeah. So yeah, my understanding is that's a difference with the CCM approach, right? Is that you don't have that same.
Yeah, it's different.
Yeah.
Yeah, so it's much weaker than that, I think. So to further verify whether it is actually causal relations, we need more assumptions or more information. Yeah.
Okay. Well, I'll let other people have a turn. Thanks.
Ian, yeah.
Thanks very much, Mingming. It's a very interesting talk.
Thank you.
I learned a lot. But it's hard for me to think about much more than the very basic examples because I'm not familiar with the area. I wanted to ask you about one of the sort of toy examples, I guess you had of 1y and 1x, where you said that you could possibly resolve a causal direction with some assumptions about the structure of the errors. But
yeah.
I don't know whether it's an observation or a question, but I take it that it is true that you are doing that with the introduction of an assumption. I mean, the whole point of such data is that you would not typically have any such assumptions. You have the X and the Y. You don't have separate assumptions about the errors. Otherwise, we're in a different world.
Yeah. So this is a assumption on the noise term.
Yeah.
So basically, I think when we have a system, yeah, we don't know the distribution of the noise, right?
Yeah.
Basically, in my view, it's usually, I think many methods that just assume the noise is Gaussian.
Yeah.
So I think non-Gaussian might be a weaker assumption than the Gaussian distribution. Yeah. But
sure.
still is assumption, but I think maybe in the real world, if the system actually have non-Gaussian error terms, then this method can be applied.
Yeah.
Yeah.
But if we just have an X and a Y, we won't typically know what assumption to make about the errors. True?
Yes.
Yeah.
It's hard to check that, but for some simple system, maybe we can check whether the noise is Gaussian or not. So I think in statistics, I know the method to check whether error terms are Gaussian.
Yeah. Sure.
So if it's Gaussian, then this method cannot be applied. If it's not non-Gaussian, we can use this information.
Okay. Thank you.
Yeah. Thank you.
So what about, just out of curiosity, kind of following on from that, what about in circumstances wherein you expect, kind of nonlinear dynamical systems, how which I don't want to reduce to just mere assumption checking, because that's kind of a substantively important case that isn't really just about checking assumptions. It's about modeling the system properly and deriving kind of time varying causal effects, for example, or whatever follows from the particular system that you're modeling. So for those kinds of systems, which probably exist in a wide variety of different fields, how are you thinking about those kinds of systems currently, and what kinds of extensions to the approaches that you've just presented do you think the future holds to address that?
Yeah, so for the if the system is nonlinear, currently we don't have a way to extend the method to address the low resolution problem. So basically to solve this low resolution problem, currently we'll only figure out the condition under the linear assumption. So in the nonlinear case, we have no guarantee that we can actually recover the true causal relation from the low resolution data. Yeah. So this means if you have a signal which might have a nonlinear relations, then you need to make sure the temporal resolution is not that low.
Yeah.
Yeah. So currently there are no method to address this problem.
One possible approach for dealing with the issue of different time lags and the different images of a dynamic system that you get when you have different time lags that's been proposed, at least in psychology and a few other fields, is intentionally varying the time lag. So you're collecting data, sometimes with a gap of, well, whatever the research design might be, sometimes a day, sometimes a few minutes, sometimes a few hours, et cetera. And then using a continuous time model, as opposed to what is traditional in VAR type applications is obviously some kind of discrete time model. And so in cases like that, I guess the idea is that because, in fact, different dynamics can emerge at different timescales, then the thinking goes, and here'd be an example of it in the chat. The thinking goes there that then what you get is obviously better coverage in terms of sampling the dynamical system. I'm just wondering if that is could be an extension
point.
of
yeah. So in my previous project, we only have the access to some low resolution time series, which is just fixed. Yeah, for example, the GDP was record yearly. Right. So yeah. Yeah, thank you, Laura.
Okay, well, it's almost 10 minutes past 3, unless anybody else has any questions or kind of burning desires here, other than to get their weekend started. We should probably stop here and say thank you again so much, and Mingming, and for a great talk. And we'll put this up on the web, and congratulations again on your DERRA. It's great for you. It's great for everybody. Mostly for you.
Yeah, thank you so much. And yeah, probably we can find the opportunity to meet in the future, right? After the campus is open.
Well, that's right. That's right. Yeah. We'll start having some meetings in person, I guess, at that point. And if you're interested in some of the logic underlying Simon Dennis's question, then we have a talk on empirical dynamic modeling, or what he also called convergent cross-mapping, on the QMNET YouTube site by one of our collaborators, Jing Li.
Yeah.
So if you're interested in that talk, it's there.
Okay. Yeah.
Okay. Thank you so much. And I'll stop it now.